Okay, so the next goal for us in 14.4 is to define the differential. This is something that you kind of spend a little bit of time in Calculus 1 talking about. The differentials are dx and dy. And you talk about it in the context of an image like this. So if you have some function y equals f of x, and let's say that this blue curve is that function, or the curve of the graph of that function. If you compute a tangent line, or come up with a tangent line at a particular point A to that curve, and then you go and increment in x. So starting from A, you add a delta x to that. That takes you this little distance right here. If you compare the point on the tangent line at a plus delta x and the point on the curve at a plus delta x, they're going to differ by a little bit. If delta x is very, very small, if this increment is very, very small, and if the blue function is a differentiable function, then we would expect this tangent line to give us a close approximation to the curve. But we define certain quantities with the change in y along our tangent line and the change in y along our curve as we go from a to a plus delta x. The change in our tangent line is what we call dy, and the change in our curve is called delta y. So the delta y you think of as the true change in your blue curve, or in your function f of x, whereas dy is kind of like an approximation to that change. Okay. So this is all covered in Calculus 1, but what we want to do is try and mimic that in the context of tangent planes now. And we do that first by defining something that we call a total differential. So again, I'm going to return to this for a second. From this image, you derive this dy is equal to f prime of x times dx. And it's really just an application of the fact that f prime of x is the slope of this function at that point. But here, we define the total differential dz in a similar way. It's fx of xy dx plus fy of xy dy. Or you can think of that as the partial of z with respect to x times dx plus the partial of z with respect to y dy, where dx and dy are defined in a similar way as they are in the single variable case. Dx corresponds to the change in x as I move from some point AB to some point A plus delta x, B plus delta y. So that means I can write delta x as x minus A and dy as delta y minus, dy as delta y, which is the same thing as y minus b. So this is the two variable analog of the picture we just looked at a second ago. And just to help you make sense of it, so here's the blue surface here is the surface corresponding to the function z equals f of xy. The yellow plane underneath it is the tangent plane to that curve at this point right here. It's the point AB, f of AB. That would be the z coordinate there. Okay? Now, you can see that from this point to the point that corresponds to a small change in x and a small change in y. So a plus delta x. I added delta x to this x coordinate. B plus delta y, adding delta y to this y coordinate. On the plane, the z coordinate at this new point is f of this, f of a plus delta x, b plus delta y. Because that's how you get points on a surface. You plug the x and y coordinates into the function to get the z coordinate. The dz is, so delta z is going to represent the change from this point on our surface to this point on our surface. The dz, by analogy to what we did in the single variable case, is going to represent the change in z from this point to this point on our tangent plane. And that is why the total differential looks very similar to the equation of a tangent plane. It's because that's what it represents, the change in this, and change in z from this point to that point right there. And as you can see, if delta x and delta y are very small, and if this blue surface is the graph of a differentiable function, then the tangent plane should give a close approximation to this point right here, using this point on the tangent plane. So we would expect dz to be a good approximation to delta z, as long as the blue curve is, or the blue function, sorry, the blue surface is that of a differentiable function. So let's do a couple of examples with differentials before we wrap things up. Z is equal to x squared minus xy plus 3y squared, and we're going to have the point xy change from 1, 2 to the point 1.05, 2.1, and we want to compare dz and delta z. Now this is a polynomial, and all polynomials are differentiable everywhere. It's very easy to show that. And so you notice this change from here to here is very small. We're expecting the comparison between dz and delta z to be very close. This should be a good approximation for this based on what we just talked about. But how do we compute that? So again, we need our dz, which is our total differential, and we get it by using this. I need to compute fx, dx, fy, dy. Okay, so what is, we're not calling it f anymore, we're calling it z, so what is zx? Zx would be 2x minus y, and then that's going to go to 0. What is zy? Zy would be negative x plus 6y. Okay? Now, we need zx of, now remember we're changing from 1.2 to this point. So in our picture up here, that's like changing from the point that we computed our tangent plane at to this point. So the AB in question here is 1, 2, not these numbers. It's 1, 2. I need zx of 1, 2 and zy of 1, 2. All right, I'm just plugging that into the partial derivative that I just found. So what would that be? That would be 2 times 1 minus 2, is that right? Oh no, do I have the right? I think I have the wrong point here. Hang on. No, that's okay. So 2 times 1 minus 2, that would equal 0. And then zy from 1 to, zy, plug that in, that's going to give me negative 1 plus 12, which is equal to 11. Okay, and then we're going to use these after we find dx and dy. So what is dx? Okay, so dx, comparing or going up here, dx is defined to be the difference in x minus a, and what this is supposed to represent is the change in x, right? So thinking of it in terms of change of x, we're going from 1 to 1.05. That means this is equal to 1.05 minus 1, or 0.05. Okay? We need dy as well. So the change in y, 2.1 minus 2, which would be 0.1. That's what we would get for that differential. Okay? So what is dz then? dz is equal to zx, which is 0, times dx, 0.05, so that doesn't contribute anything because of the 0, plus what I got for zy, which was 11, times 0.1, my dy. Okay, and this is just equal to 1.1 after simplifying everything. Okay, now what I need is delta z. So what is delta z? Delta z is what I would get from plugging in the true the point that I'm actually moving to directly into this function, and then subtracting what I would have gotten from plugging 1, 2 directly into that function. Remember, delta z is not just the z coordinate of this point, it's the difference between the z coordinates of these 2 points. So let's start by plugging in this one. I'm going to get 1.05 squared minus 1.05 times y, which is 2.1, plus 3y squared. So that's 3 times 2.1. And I'm going to subtract from that what I would have gotten by plugging 1, 2 into this function. So that's going to be 1 squared minus 1 times 2 plus 3 times 2 squared. Okay? Oops, there we go. I'm actually going to leave this part to you. So I have dz here. We compute delta z by plugging this into a calculator, but try this. Plug this into a calculator and give me what this is equal to. I don't know why I put it approximately, but check it compared to this. These two values should be pretty close together if we did this right. Okay? When I'm teaching in person, I usually will have the students do part of the example with me, and then we talk it out. I can't talk it out with you in this way, so I occasionally do want to leave things for you to kind of finish and sort of experience for yourself why these results are working out the way that they are. Okay, last example. This is something that should feel a little bit familiar from Calculus 1, kind of an application of differentials. We can use them to approximate certain things that appear in like a physical context. So here's this example. We want to use differentials to estimate the amount of metal in a closed cylindrical can that is 10 centimeters high and 4 centimeters thick in diameter if the metal in the top and bottom of the can is 0.1 centimeters thick and the metal in the sides is 0.05 centimeters thick. Okay, so if you can kind of picture a can like this. It's 10 centimeters high. The diameter is 4 centimeters, so that means the radius is 2 centimeters. And then we're told the thickness of the metal. So we're specifically being asked not for the volume of the can itself, but the amount of metal, which is still a volume, but it's the volume in terms of the amount of metal used to make this cylinder. Okay, so the thickness of the tops and the bottoms, which you can't see in my picture, but the thickness is 0.1 centimeters. 0.1 centimeter. The thickness of the material that's being used in the sides is 0.05 centimeters. So if we were to, say, cut this can up and lay all of its metal out flat, we want the volume of that metal, basically. Okay, but even though we can compute that exactly, we want to try and approximate it instead using differentials. So let's consider how you find the volume of a cylinder in the first place. What is the volume formula for a cylinder? It's pi r squared h, right? Now, if you think of it, there's the inner portion of the cylinder, which is like the part that's empty, the part that you would pour something into. And then you can think of the outer portion, which is like the outside of the surface. And those two things are separated by these thicknesses. So you can think of this 0.1 here and this 0.05 here as representing a change in height and a change in radius for this cylinder. And where am I going to get those changes? Well, using our formula for the total differential, I want dV, right? That's the differential, the total differential for volume. Now, notice this is telling me that V is a function of R and H. So thinking about how we find the total differential, I want to differentiate V with respect to my first variable, R, and multiply that by dr, plus the differential with respect to the other variable h, which I multiply to dh. That's just using the formula for our total differential. Okay? Now, can I find dr and dh from the given information? Yes. dr corresponds to a change in my radius. As I move from the kind of interior of this can to the exterior of this can, going through the thickness of that metal, we go 0.05 centimeters. That would correspond to the change in my radius. What is the change in my height? Okay, well, the change in height would correspond to the change in thickness in not just the base of my can, but also the top of my can. Because again, if you move from the empty interior to the metallic exterior, you're moving 0.1 centimeters up and 0.1 centimeters down. So that's 0.1 plus 0.1, which is 0.2. That's what dh would be. Okay? We also have that r is equal to 2, and h is equal to 10. Okay, those are the dimensions that are given to us for the actual radius and the actual height in the problem. Now, I need to compute these derivatives, these partial derivatives. Partial of v with respect to r, partial of v with respect to h. So let's do that next. What is the partial of v with respect to r? Well, I have a function here that I can do that differentiation with. Differentiating this with respect to r gives me 2 pi r h. And if I differentiate with respect to h next, that's just going to give me pi r squared. Okay, pi r squared. Now, I'm supposed to be plugging in values for these, right? Because we want the partial of v with respect to r, where r is equal to 2 and h is equal to 10. So this is like at the point 2, 10. If I plug a 2 in for r and a 10 in for h, what do we get? That would be 40 pi, right? It'd be 40 pi there. And then let's see. Just make sure I'm plugging these in the right way. If I find the partial of v with respect to h, which we just found, and plug 210 into this guy, so now r is the only variable making an appearance. This becomes 4 pi. All right. So looking at my differential now, dv, we can use all 4 of those things that we just found in that formula. That means dv is equal to this guy, 40 pi, times dr, which was 0.05, plus this next guy, 4 pi, times 0.02. That was dh. Okay, that goes into a calculator, and we get an approximate value of about 8.792 cubic centimeters of metal. Okay, so that's it for 14.4.